Welcome back. The last few videos we have seen one example of regular Sturm-Liouville system to find the eigenvalues and eigenfunctions, and rest an examples for periodic and singular Sturm-Liouville systems we have seen. Today we just have we'll have two more examples of different way of finding eigenvalues and eigenfunctions for the regular Sturm-Liouville system. So, to start with the first example, which I explained in the last video. So, we can see this this is the example so for which you can find eigenvalues and eigenfunctions. It's a little different from the what we have done for the first example of regular Sturm-Liouville system. So, you need to take the differential equation plus lambda y equal to 0. So, this you want to put it in this Sturm-Liouville form. So, self-adjoint form or Hermitian form or skew symmetric form. So, whatever you say. So, x is between 0 to pi. This is what is the domain. You need to put this together as a derivative of something. So, to do this, this is just a linear equation of type, right. So, if you think of y dash as a dependent variable, you have dy dash by dx minus 2 y dy by dx. Okay. So, that dy dash by dx minus 2 y dash. So, for y dash this is a linear equation. So, you know that integrating factor is e power integral p is here minus 2 dx. So, you have e power minus 2x. That is the integrating factor for this these two terms. So, if you multiply to this equation e power minus 2x, so e power minus 2x y double dash minus 2 e power minus 2x y dash plus lambda into e power minus 2x y equal to 0. So, x is between 0 to pi. Now, I can put this with the multiplication of the integrating factor. I can combine these two together as a derivative of e power minus 2x y dash or dy by dx. Okay. So, you can see that e power minus 2x y double dash, and if you differentiate this you get e power minus 2x into minus 2 into e power minus 2x y dash. So, plus q is 0 and you can put this as outside a minus, and this will be lambda into e power minus 2x y. Okay. So, this is actually your Ly as a definition. So, x is between 0 to pi and L is minus d dx. Now, p is minus e power minus 2x, okay, and q is 0. So, 0 into 0, simply q is 0. So, we do not write this. So, this is what is, once you identify this operator, you can write the dot product of two functions. Here is the definition is from the domain, which is 0 to pi, and so w is you have a w here. So, e power minus 2x. So, you can just divide with this. Okay. So, you can write 1 by e power. So, you can bring this e power minus 2x this side. So, it is going to be plus. Okay. It is going to be plus. So, you can remove this. So, where L is 1 over e power minus 2x. So, this is your w. So, w is this into fx gx bar dx. This is the dot product you have. So, this is what is your Sturm-Liouville equation Ly equal to lambda as an eigenvalue problem. Okay. So, you need to find the eigenvalues and eigenvectors. Now, consider. So, consider now L is the self-adjoint form. So, you have Hermitian form implies lambda is real since L is in Hermitian form or skew symmetric form. So, you can now consider. So, lambda is real means you can be positive, negative, all such things. So, first consider the general solution of the equation, given equation. So, that is y double dash minus 2y dash plus lambda y equal to 0. Okay, so this one, what are the solutions? This is a linear equation with constant coefficients. You can look for solutions in this form, e power kx. If you look for in this form, if you put it, you get k square minus 2k plus lambda equal to 0. So that will give me what are my k values, 2 plus or minus square root of b square minus 4 lambda divided by 2. So this will give me 1 plus or minus square root of 1 minus lambda. So these are your roots. So implies you have this general solution. General solution is yx, which is a second order equation. So you can get the general solution as some c1 times, and you see that this is a c1 times e power 1 plus square root of 1 minus lambda into x plus c2 e power 1 minus square root of 1 minus lambda into x. So this is your general solution. Now, so you know that lambda is real. We'll just start with, because you see it involves the general solution involves 1 minus lambda. So let's consider first lambda is equal to 1. Okay. So we can also think if it is not there, so you can also look at lambda positive, lambda negative, and lambda equal to 0. Because it has a term 1 minus in the solution, you have square root of 1 minus lambda. That suggests you work with lambda equal to 1 first. So if you put lambda equal to 1, what's your general solution? So what happens to your roots? If lambda equal to 1, what you get is k square minus 2k plus 1 equal to 0. So you have k minus 1 whole square equal to 0. That will give me k is 1 and 1. So you have repeated roots. So the general solution is e power c1 e power kx, that is 1x, k is 1. So you have e power x plus c2 x into e power x. Okay, so this is what you have. Now you apply your boundary conditions. What you have is, starting with the first boundary condition, y0 is 0. If you apply here, so y0 is 0. So you have c1 1. So c1 plus c2 into 0. So that is 0. So this is 0. So you will get c2 is 0. c1 will be 0. So this implies the general solution becomes c2x e power x. Now you can apply other boundary conditions. So apply the other boundary condition, that is you have y pi equal to 0. See, if you apply this, you get c2 pi e power pi has to be 0. This is possible only if c2 is 0, right? So you have c2 is also 0. This is possible because this is non-zero, so c2 has to be 0. So the general solution, finally, that implies general solution, or the solution satisfying these boundary conditions, becomes yx is identically 0. So that means lambda equal to 1 is not an eigenvalue. Okay. So you can look at lambda greater than 1 and lambda less than 1. You have three cases that you can look at lambda greater than 1. If you look at lambda greater than 1, then in that case, this is your general solution and this will be I. Okay. So when lambda is greater than 1, the general solution of the equation yx equal to, so e power x is common. So you can look at this e power 1x, e power 1x, e power 1x is common. So you can take this out and you have c1, and what you get is when lambda is greater than 1, 1 minus lambda is negative. So you have lambda minus 1, I times square root of lambda minus 1, lambda is greater than 1. So you have c1 e power minus or you can rewrite. So you have that involves e power I square root of lambda minus 1 x, here e power minus I square root of lambda minus 1 x. So that you can write also as a linear combination of cosines and sines. So we will write as a cos lambda minus 1 x under root, of course, square root of lambda minus 1 into x, okay, and then plus c2 sine square root of lambda minus 1 into x. X is outside, okay. So this is your general solution. Now we apply the boundary conditions. y0 0 will give me, what happens to 0? E power 0 is 1, c1, that is c1, plus c2, this is when you put x equal to 0, that is 0. So this is what you get, c1 is y0, which is equal to 0. So you get again c1 is 0. So the yx becomes e power x c2 sine square root of lambda minus 1 into x, okay. So now we apply other boundary condition, y pi is 0, that will give me e power pi c2 e power pi sine lambda minus 1 into pi equal to 0. So this is non-zero, this cannot be 0, and this can be 0 for some lambda values, for lambda greater than 1. So we have to see what those values, okay. So if such lambda values, c2 can be arbitrary. So you can take this lambda minus 1 into pi equal to 0 will give me square root of lambda minus 1 pi equal to n pi. And you see that this quantity lambda is greater than 1. So this should be running from 1, 2, 3 onwards. Reason is n equal to 0. If I take n equal to 0, then it will become 0, that is lambda equal to 1, which I have already seen that is not an eigenvalue. If I take n negative, then lambda minus 1 is actually cannot be negative, okay. So it has to be positive. So this is what you have. So these sign values, positive values, so square root of this number should be positive. So right, so you have this. So this implies you have lambda minus 1 under root is n. This will give me lambda as n square plus 1. N is running from 1 to onwards. So these are your eigenvalues. Lambda n equal to n square plus 1 and eigenvalues for which you have non-zero solution. So you have C2 can be arbitrary, so you can take it as 1 e power x for these lambda values. If you put it, so eigenfunctions will be, you call them Vn of x, which is e power x sine root lambda minus 1 is n. So you have sine nx. So for both n is running from 1, 2, 3 and so on. Even if we put n equal to 0, actually becomes, you see that Vn is 0. So it is not an eigenvalue, corresponds to lambda 0 equal to 1. So these are your eigenvalues and eigenfunctions when you consider lambda greater than 1. So you have another case, that is lambda less than 1. If you consider this case, the general solution you can rewrite. So yx is e power x is common. So you have c1 e power, when lambda is negative and lambda is less than 1, and this will be positive, okay. So this will be positive, so you can write as it is. So you have, simply write 1 minus lambda x plus c2 e power minus 1 minus lambda x, okay. So now you apply the boundary conditions. Y0 is 0 implies c1 plus c2 equal to 0, okay. So it will give me c1 equal to minus c2. So implies yx equal to e power x, c1 you can take it out, e power x is common. What you have is e power square root of 1 minus lambda x and you have C2 I am replacing with minus C1. So, you have a minus e power minus square root of 1 minus lambda x. Okay. So, this is what you have. So, this is your general solution after applying the boundary condition 1. Now, you apply the other boundary condition y pi is 0, you get C1 e power pi e power square root of 1 minus lambda pi minus e power minus square root of 1 minus lambda pi. So, this quantity has to be 0, and you see that this is e power something. If you fix lambda less than 1, this is some finite number. So, e power, call this some c pi minus e power minus c pi, there will never be 0. So, this cannot be 0 and this cannot be 0, that means C1 has to be 0. So, that implies yx is identically 0, that implies lambda less than 1 is not an eigenvalue, because you do not have non-zero solution for the system. So, what you have found is only these are your eigenvalues and these are our eigenfunctions. So, any piecewise function, any piecewise continuous function f(x), which is the domain between 0 to pi, I can be written as Fourier series. The Fourier series is f(x) is from n is from 1 to infinity, you have some Cn, and what are your eigenfunctions? E power x sin nx, e power x sin nx, okay, where Cn's you simply integrate. So, take the dot product where Cn's are. How do you find my Cn's? You just take the dot product with Vn's, e power x sin nx sin mx equal to, so when you multiply this e power x sin mx, only Cm will be contributing, n equal to m only will contribute. So, you have e power x dot product sin nx mx e power x sin mx, okay. That is Cm is integral 0 to pi, you have e power minus 2x is your weight function, e power minus 2x f(x) e power x sin mx dx. So, this e power x and e power minus 2x will go. So, you have e power minus x this divided by, now this one you integrate 0 to pi e power minus 2x e power x sin mx whole square. So, when you whole square, this is what you get. So, this will go. So, what you get is this this quantity is simply, because integral 0 to pi sin square mx dx is, you can write 1 minus cos 2 mx divided by 2 from 0 to pi, that value is pi by 2, just a half that you put the limits 0 to pi. So, you have pi by 2. So, you have 2 by pi, Cm is 2 by pi 0 to pi e power minus x f(x) sin mx dx. So, that is what is your Cm. So, these are your Fourier coefficients for Fourier transform. Fourier transform with this with respect to these eigen functions. Now, this is your Fourier series. Okay. So, because it is something to do with some other some other example, it is not from in terms of sine and cosines. So, you can say that is generalized Fourier series. Okay. You can say generalized Fourier series is a generalized Fourier transform. For this particular example, you got a Fourier type of transform and series. Okay. And this way, for a piecewise continuous function f(x), this convergence of this series is actually pointwise. You fix x, this series as a series of numbers converges to the function value at that point. Okay. So, we look at some other example of regular Sturm-Liouville system, in which case we may not be able to get explicitly your eigenvalues. Okay, let us see that example. One more example with that we will wind up this Sturm-Liouville theory. So we can have so what you consider is now find eigenvalues and eigenfunctions for this regular Sturm-Liouville system. Regular Sturm-Liouville system, that is y double dash plus lambda y equal to 0. Lambda is the parameter, and you have the domain is between 0 to 1, x is between 0 to 1, and you have y0 is 0 and y1 minus y dash 1 equal to 0. So because it is a regular Sturm-Liouville system, you can give, this is simpler one, but this is a combination of its derivatives. So you have chosen combination of y and its derivative at 1 is equal to 0. So if you have like this, always when you take the combination, you may not be getting solution eigenvalues explicitly. We will see how it is. So you write this as y dy by dx of d dx is minus equal to lambda y. This is my ly. Okay, so x is between 0 to 1. So it's already in the self-adjoint form. So L is minus d dx of d dx, p is 1 into d dx, and w is 1, q is 0. So dot product of I can define dot product here. This system is 0 to 1, w is 1, so you have simply fx dx bar dx. So what happens now? We find the, so now it is in self-adjoint form, so lambda is real since L is self-adjoint. L is self-adjoint or Hermitian, or you can say skew symmetric. Now you can look at all different cases. Okay, so lambda is either positive, lambda equal to 0, or lambda less than 0. So you look at all these cases. Okay, so start with lambda positive. If you take this one, if lambda is positive, so we have y double dash plus lambda y equal to 0. So lambda positive means lambda equal to mu square, mu is positive. So as usual we can think of like this, you can put lambda equal to mu square. So you will get general solution. General solution yx is c1 cos mu x plus c2 sin mu x. So this is a general solution, okay, between x is between 0 to 1. So now we apply the boundary conditions like earlier. So you have y0 is 0 will give me c1 is 0, c1 0, that is 1, cos 0 is 1, plus c2 into 0, that is 0. So I have c1 which is equal to 0. So you have c1 is 0. So the general solution becomes now c2 sin mu x. Now you apply other boundary condition, that is y at 1 minus y dash at 1 equal to 0. If you apply this boundary condition here, for this you have c2 sin mu minus c2 mu cos mu into 1. So that is, this has to be 0. So this is nothing but sin mu minus mu cos mu has to be 0. So I just have to see for those mu positive values for which this quantity is 0. If no such value satisfying this equation, that means C2 has to be 0. That means all mu positive are not an eigenvalues. But we have to see this one. This is called dispersion relation. So sin mu minus mu cos mu, whether it has any positive mu solutions. So this is actually tan mu equal to mu, right? You can just divide thinking that cos mu so you can rewrite this tan mu equal to mu, right. So, sin mu divided by cos mu, that means cos mu should not be 0, right, and cos mu equal to 0, that is you know that these are pi by 2, 3 pi by 2 and so on. So, these are the values, we know that this quantity is not 0. Okay. So, this except that this has to be 0, cos mu should not be 0 when you do this one, when you divide. Suppose it is 0, okay. Suppose if it is 0, that is true only at these values, but these values you can easily see that this quantity is non-zero. So, these mu pi by 2, 3 pi by 2, this quantity is non-zero. So, you can think of other values, you can divide it and you can now find the roots of tan mu equal to mu. Okay. So, this we do graphically. This is like let us say mu is here, this is like tan x equal to x. Okay. This is your y equal to mu is, y equal to x is something like this line, and now you have tan mu, that is tan x, y equal to tan x. So, tan 0 is 0, tan pi by 2 is, only you want a positive side, tan pi by 2, tan pi, tan 3 pi by 2 and 2 pi and so on. So, for this you have things like this, we will say at pi by 2 it is going to infinity. So, you have something like going to infinity at pi by 2. Other things you will have tan, what is the other value? So, that is tan pi. What is tan pi? Sin pi by cos pi. So, that is 0. So, it should be 0 here, and here at pi by 2 the negative side it should go to it should nicely go to eventually asymptotically it should go to minus infinity. At 3 pi by 2 this should go to asymptotically minus infinity. Again at 2 pi by 2, and 2 pi plus pi by 2 is 5 pi by 2, and again here you have something like this curve. Okay, this is at 2 pi. So, like this you get. So, you see that this curve and this curve is touching at these points, okay, and this is 0. So, we do not consider. So, this is your, because mu is positive, so you have to worry about only this one. This is your mu 1, this is your mu 2, like this and so on. You can denote them like that. So, and say then let mu 1, mu 2 and so on be the roots of, you have roots, that is clear from this graph, tan mu equal to mu. Then lambda is mu I square, I is from 1, 2, 3 and so on. Okay. That is your lambda i's. These are your eigenvalues for which C2 is arbitrary. Once C2 is arbitrary, so you have yx is sin mu x. Sin mu x are, those are your vi of x. These are your eigenfunctions, sin mu I x. So, these are eigenvalues. Then these are eigenvalues. So, this and this are eigenvalues and eigenfunctions respectively. This corresponds to eigenvalues, this corresponds to eigenfunctions. So, you do not know explicitly exactly what are your mu i's, some values, okay, wherever. So, you can numerically you can find out all these values, mu 1, mu 2, mu 3 and so on, they are all positive. Okay. So, I found certain eigenvalues and eigenfunctions corresponding to the case mu positive, that is lambda positive. Now, look at the lambda equal to 0 case. Now, you know that general solution of the equation is y double dash is 0 is the equation when lambda equal to 0. So, the general solution is C1x plus C2. You apply the boundary condition y0 is 0 will give me C1 into 0 plus C2. So, that will give me C2 is 0. Okay. So, yx becomes C1x. Now you apply the other boundary condition, y at 1 minus y dash at 1 is 0. So, this will give me C1 minus C1, this derivative, that is also C1, which is 0. It is satisfying. So, you see that you take any arbitrary value of C1, so that means non-zero value of C1, it is actually satisfying a second boundary condition, it is satisfied. Okay. So, that means, so this is something like see what you have is C1 times 1 minus 1 equal to 0. So, you have C1 times 0 is 0, that means C1 is arbitrary. Once you have C1 arbitrary, your general solution is this one. So, you have a non-zero solution. So, this implies lambda equal to 0 is an eigenvalue, and so you call this lambda 0 corresponding to I equal to 0. So, V0 of x corresponding eigenfunction I am denoting as V0, which is you can take C1 as 1. So, you have this is x is corresponding eigenfunction. Now, look at the case lambda negative, that means lambda equal to minus mu square with mu positive. In this case, what is your y double dash minus mu square y equal to 0. This is how the equation becomes. The general solution is of this equation is C1 e power mu x plus C2 e power minus mu x. You apply the boundary conditions now, will give me C1 plus C2 equal to 0, that will give me C1 equal to minus C2. This implies solution becomes, general solution becomes C1 times e power mu x minus C2 I am replacing with minus C1. So, you have e power minus mu x. Okay. So, now you apply, this is actually equal to C1 to C1, and this is sine hyperbolic mu x, mu is positive. Okay. So, now you apply the other boundary y at 1 minus y dash at 1 equal to 0 will give me, for this you have 2 C1 sine hyperbolic mu minus 2 C1 mu cos hyperbolic mu equal to 0. So, this will give me 2 C1, 2 cannot be 0. So, this has to be C1 times sine hyperbolic mu minus mu cos hyperbolic mu has to be 0. So, I just have to check whether for some positive mu values this quantity is 0. So, again you do the same thing. So, to check this sine hyperbolic mu minus mu cos hyperbolic mu equal to 0, that is you can do if this is tan hyperbolic mu equal to mu if cos hyperbolic mu is not equal to 0, because you are dividing with it, but this will never be 0, right? This will never be 0 for any mu positive value. So, actually you can do it. Okay. It is not just if, because since this is non-zero you can always divide. Now, you look at this tan hyperbolic plot and this y equal to mu plot, this is y equal to mu, and you plot tan hyperbolic mu, they never touch anywhere. Okay. If you just do it, they do not touch any other place. So, you can plot it and see tan hyperbolic mu, you do not have any solution, non-zero solution. Okay. Positive solution, strictly positive mu, you do not have any solution, actually touching and above it goes, simply goes above, only at touching at 0. This is the only road, but that is mu is equal to 0. So, implies for non-zero mu, no non-zero, no non-zero mu satisfying tan hyperbolic mu equal to mu. That means, that implies for mu positive, this quantity sine hyperbolic mu minus mu cos hyperbolic mu is non-zero. That means, by looking at this, C has to be 0, C1 has to be 0. That implies the general solution becomes, earlier after applying the first boundary condition your general solution is this, now that you found C1 is 0, that means completely 0 between 0 to 1. That means lambda negative is not an eigenvalue. Any lambda negative is not an eigenvalue. So, what you found is finally you have this is one eigenfunction corresponding to 0 and the other eigenvalues and eigenfunctions which found mu i's, sin mu i's. Mu i's are satisfying tan mu equal to mu. So, now you know what are your eigenvalues and eigenfunctions. As usual, you can write the Fourier transform and Fourier series in this case. So, any piecewise continuous function f(x) which is defined between 0 to 1 is written as f(x) which is equal to, now what you have, it is running from I is running from 0 to infinity, 1 to infinity what you have for lambda positive, and I lambda equal to 0 correspond to I equal to 0. So, you have Ci and what is your functions Vi's. So, those are sin mu I x and x, you have two such things. So, you can rewrite like C0 into x, that is 1 corresponding to lambda equal to 0, and these things you can sum it up with n is from 1 to infinity, and you have Cn and sin mu n x. Okay. So, you have these are your eigen functions sin mu I x. So, I am just change the index as n. Okay. Where Ci, so how do you get your C0? C0 you should get it from by, this is your eigenfunction, this is your eigenfunction. So, by multiplying this eigenfunction x and take the dot product with f, you can get your C0 xx. Okay. And this, if you take your dot product with sin mu nx, mu nx, or you write mx, you can get Cm dot product with sin mu mx sin mu mx. Okay. So, what are these? You can think of, so that is C0 is now integral 0 to 1, I do not have, so the weight function is only 1, so it is usual dot product fx into x dx between 0 to 1, this real bar does not matter. So, you have divided by integral x square. So, you have to write 0 to 1 x square dx, that is x cube by 3 between 0 to 1. So, it is 1 by 3. So, you have 1 by 3. So, you have total 3. So, you finally get C0 as this one between this, and Cm as integral 0 to 1 fx sin mu mx dx divided by this, because you do not know what is exactly your mu m, you cannot you may not be able to, you can actually find sin square mu m x dx. This you can calculate and put it, this is how you find these. So, these are your Fourier transform, generalized Fourier transform, and this is your Fourier series. You can think of fx as a signal, you can split it into discrete frequencies. At these frequencies you have these solutions. Okay. These are your discrete frequencies. So, you have 1 to 0 to infinity. So, at every frequency you split the signal. Okay. So, you have this is a Fourier transform, and you can get back your signal by combining all of those discrete frequencies, okay, with these functions. So, this is how you can get eigenvalues and eigenfunctions. Here you got implicitly, so you could not find explicitly these eigenvalues and eigenfunctions, right. So, this is the example that will tell you a story. So, this is the Sturm-Liouville theory. So, what you learned from the Sturm-Liouville theory is this is just the property of second order linear differential equation, okay, ordinary differential equation. So, using this you can develop actually what is a Fourier transform and Fourier series of a function defined on a finite interval. So, if you think of this as a function over a real line which is a periodic function, okay, and that finite interval is whatever is defined repeated everywhere as a periodically. So, such a thing you can represent as a Fourier series in terms of eigenvalues and eigenfunctions rather. Okay. So, another use of this Sturm-Liouville theory is you try to extract this Sturm-Liouville problem when you solve partial differential equations in a simpler domains, that we will do in future videos. Okay. So, when you are solving these partial differential equations in a simpler domains such as rectangular or circular or elliptical domains, you may have to convert. So, you may have to extract. The main idea is to how do we solve this partial differential equation. The idea is to extract, if you can extract a Sturm-Liouville problem out of that boundary value problem, whatever you have for the partial differential equation, then you get all the solutions, eigenvalues and eigenfunctions of the corresponding whatever you get extracted Sturm-Liouville problem. Using them, you combine them, you make a general solution of the PDE and get back your unknowns. Take a linear superposition because it is a linear equations. You can only solve linear partial differential equations on a simpler domains using this Sturm-Liouville problems. That we will see in the next videos.